Tonight, imagine aiming the most powerful infrared space telescope ever built at one of the brightest stars in our cosmic neighborhood. You block the star itself. You remove its glare. You search the darkness beside it for something colder, fainter, and almost impossibly small. Then a point of light appears. It sits near Alpha Centauri A, a star strikingly similar to our Sun, only a little more than 4 light-years away. The point is not another star. It does not behave like an obvious background object. And if the signal is really a planet, it may be roughly Saturn-mass, circling within a region where a rocky world could receive temperatures compatible with liquid water. That sounds like a discovery. But then James Webb looked again. The point was gone. And when Webb returned a third time, it was still missing. By the end of tonight, we'll follow that disappearing signal from the first image to the strange orbital possibility that could explain where it went, and why this may be one of the most important unfinished planet hunts ever attempted. If calm investigations like this are your kind of night, you can subscribe. Now, let's begin. Alpha Centauri is the place where science fiction starts feeling uncomfortably close. Walk outside on a clear southern night and to your eyes the system looks like a single bright star. But it is really a family. Alpha Centauri A and B circle each other in a long stellar dance, while the small red dwarf Proxima Centauri travels much farther out. Proxima already has known planets. Alpha Centauri A is different. It is one of the nearest stars that genuinely resembles the Sun, that makes the empty space around it unusually important. If planets formed there, we would not be studying some exotic system around a tiny red dwarf. We would be looking at planetary architecture around a star much more familiar to us. There is one brutal problem. The star is bright. A planet beside Alpha Centauri A would be like a warm grain of dust floating next to a stadium floodlight. The planet does not shine by nuclear fusion. It mainly reflects starlight and releases heat absorbed from its star. From Earth, the two sources are packed into an angle so small that separating them becomes an exercise in suppressing light with almost absurd precision. That is where Webb's mid-infrared instrument enters the story. Instead of trying to see a planet mainly by reflected visible light, MIRI can search for thermal infrared radiation. Think of standing outside after sunset. A black road may look dark, yet it still releases heat stored during the day. A mature giant planet does something similar. It can be visually faint while still glowing in wavelengths our eyes cannot see. Webb also used a coronagraph. The idea sounds simple. Put a mask over the star and reveal what is beside it. In reality, the star refuses to disappear cleanly. Light bends around edges. Telescope optics leave structured patterns, tiny imperfections create false shapes, and Alpha Centauri B adds another bright source nearby. The team had to subtract not only the overwhelming light from Alpha Centauri A, but also contamination from its stellar companion. This was not taking a photograph. It was removing a mountain of light and asking whether one warm pebble remained underneath. Webb observed Alpha Centauri A at 3 separate times: August 2024, February 2025, and April 2025. The observations used MIRI around a wavelength of 15.5 micrometers, where a cool giant planet could stand out more clearly against the star. And in the first epoch, something survived the subtraction. The researchers called it S1. It appeared about 1.5 arcseconds from Alpha Centauri A. At the system's distance, that corresponds to a projected separation of roughly 2 astronomical units. In familiar terms, imagine moving Earth outward until its orbit was about twice as wide. That is the neighborhood where the signal appeared. The object was faint, but not random-looking. The team tested whether it could be a distant background source lying by chance in the same direction. That explanation did not fit. A foreground object also failed to explain it. Tests of the instrument and image processing behavior made a simple detector artifact less convincing as well. So the possibility became harder to ignore. Maybe Webb had actually seen a planet. The estimated properties were remarkable. If S1 is planetary, models allow something roughly comparable in radius to Jupiter, but much lighter in mass, perhaps in the broad neighborhood of Saturn. Its temperature could be around 225 Kelvin. That number sounds abstract. So picture a world far colder than Earth, wrapped in deep atmosphere, receiving enough energy to remain a cool giant rather than a frozen rogue drifting between stars. The planet itself would not be a second Earth. A gas giant has no ordinary solid surface where oceans could but its location changes the meaning. The candidate may travel through Alpha Centauri A's habitable zone. That phrase is easy to misunderstand. A habitable zone does not mean a planet is habitable. It only describes a range of distances where a suitable rocky planet, with suitable atmospheric conditions, might maintain liquid water on its surface. A Saturn-like giant inside that zone would therefore be an unexpected resident, not an Earth twin. And it raises a more interesting possibility. Large planets can have moons. We do not know whether this candidate exists, much less whether it has satellites, but in our own solar system, giant planets carry entire systems of moons around them. If a cool giant really circles Alpha Centauri A at temperate distances, then the architecture around the nearest sun-like star becomes much richer than a single fuzzy point in an infrared image. But science does not get to keep a planet because the story is exciting. It has to find the object again. When Webb returned in February 2025, S1 was absent. Then came April. Still nothing. At first glance, that sounds devastating. A real planet should not simply switch off. Yet an orbit can move a planet into exactly the wrong place. Imagine trying to photograph a moth circling a porch lamp while holding a coin in front of the bulb. At one moment, the moth appears outside the coin. Later, it passes behind the blocked region or into the remaining glare. The moth still exists. Your instrument has simply lost the geometry needed to separate it. The team tested families of possible orbits. Some allowed the candidate to move into regions where Webb's sensitivity was poor during both follow-up visits. If S1 is also related to an earlier candidate signal seen by the VLT in 2019, the combined data permits stable orbits lasting roughly 2 to 3 years, with a significant chance that the planet would have escaped detection during both later Webb observations. So the disappearance does not confirm the planet, but it does not kill it either. That leaves us in a rare and uncomfortable position. Webb may have captured thermal light from a giant world around the nearest sun-like star at a separation no directly imaged planet has previously made easy to reach. Or we may be watching a much subtler false signal survive an extraordinary chain of tests. The difference between those possibilities is not philosophy. It is another image. And that is where this story becomes even more difficult, because Alpha Centauri A is not sitting alone in clean darkness. It is part of a moving binary system, filled with glare, orbital constraints, and narrow windows where a planet can hide almost in plain sight. If S1 is real, then it is not orbiting a lonely star. That changes almost everything. Alpha Centauri A has a companion Alpha Centauri B, and the two stars orbit one another roughly every 80 years. From far away, they can look like a single bright point. Up close, they are two separate suns moving around a common center of gravity, repeatedly changing the geometry of the space between them. Picture standing on a frozen lake while two enormous trucks circle each other on the ice. You are trying to place a small marble into a stable path around one truck. Most of the time, the second truck is far enough away that the marble mainly feels the gravity of the first, but the second truck never stops pulling. Its influence stretches across the system, slowly tugging, reshaping, and testing every orbit. A planet around Alpha Centauri A therefore lives inside a gravitational boundary. Too far from A, and the companion star can disturb the orbit strongly enough that the planet may eventually be scattered, captured, or thrown into a path that cannot survive for billions of years. Closer in, the situation becomes calmer. Numerical studies of the Alpha Centauri system find that planets orbiting either A or B can remain stable inside roughly 3 astronomical units under suitable configurations. That is important because the Webb candidate appears to sit inside that broad, stable region. 3 astronomical units sounds large. In our solar system, it would stretch from the Sun past Earth, past Mars, and well into the asteroid belt. But around Alpha Centauri A, that space is not empty territory. It is a protected island carved out inside a much larger binary system. And S1 may be moving through the middle of it. The Webb team's orbital simulations allow the candidate to travel on an elliptical path, roughly between 1 and 2 times the Earth-Sun distance from Alpha Centauri A. The precise orbit is not known. We have, at best, a tiny number of snapshots, but those snapshots are enough to create families of possible paths. This is where the disappearing act begins to make physical sense. When you see a planet in a direct image, you do not see its entire orbit. You see one projected position. Imagine holding a dinner plate at arm's length. Now tilt it until the plate becomes a thin oval. A bead moving around the rim might actually stay the same distance from the center. Yet from your viewpoint it can appear to rush inward, crawl sideways, or pass almost directly in front of the middle. Planetary orbits do the same thing. The true path exists in 3 dimensions. The telescope receives a flattened version, so S1 could move a substantial distance through its orbit while appearing to slide toward the region hidden by Webb's coronagraph. The planet would not become colder. It would not shut off. It would simply enter a patch of the image where the star's residual glare and the instrument's geometry make detection much harder. That is a strange kind of blindness. Webb can detect galaxies whose light has crossed the universe for more than 13 billion years, yet a possible planet only about 4 light-years away can vanish because it moves a fraction of an arcsecond in the wrong direction. Distance is not the only enemy in astronomy. Contrast can be worse. Put a candle on a mountain thousands of kilometers away and darkness surrounds it. Now put the same candle beside the sun. The candle has not changed. Your problem has. Alpha Centauri A is doing exactly that to S1. And the second star makes the scene messier still. Alpha Centauri B contributes its own light pattern to Webb's images. The researchers had to model and subtract contamination from both the target star and its companion before judging what remained. The candidate only emerged after that careful suppression of starlight. Think about what this means for the first detection. We are not looking at a bright planet floating cleanly against black space. We are looking at a faint residue extracted from a battlefield of diffraction, thermal emission, telescope optics, stellar glare, and a second nearby sun. That is why one detection is not enough. But one detection can still be extraordinary if the alternatives become increasingly difficult. A background star would sit much farther away and should behave differently as Alpha Centauri races across our sky. A nearby solar system object would also move according to a different geometry. Instrument artifacts can imitate compact sources, but repeated tests can reveal whether those patterns track the telescope rather than the sky. S1 survived enough of those checks to remain interesting. Then orbital motion created the perfect scientific frustration. The follow-up images did not give a clean yes. They also did not give a clean no. Instead, the possible planet moved into uncertainty. And uncertainty has structure. The researchers generated possible orbits that match the original position while remaining dynamically plausible around Alpha Centauri A. Many of those paths put S1 inside regions where Webb would struggle to recover it during the February and April 2025 observations. In other words, the non-detections are not random excuses added after the fact. They can arise naturally from orbital geometry. That does not prove the object exists. It means the disappearance is testable. A real orbit predicts where the candidate should move next. As months and years pass, the families of possible locations spread, overlap, and eventually narrow when new observations arrive. Each image becomes another pin pushed into an invisible track. 1 pin tells you almost nothing. 2 begins to suggest motion. 3 can start revealing a curve. And a curve can become an orbit. This is the difference between seeing something and discovering a world. A confirmed planet must return. It must appear where gravity says it should appear. Its brightness must make physical sense. Its motion must belong to Alpha Centauri A. And eventually, separate methods may be able to test whether the star itself responds to the planet's pull. But there is another reason this orbit matters. The candidate is not merely close to Alpha Centauri A. It may occupy one of the most scientifically provocative regions around the star, the zone where temperatures could allow liquid water on a suitable rocky surface. Again, S1 itself is probably not such a surface. If it is a Saturn-like gas giant, you would fall into deep atmosphere long before finding anything resembling ground. Yet giant planets are rarely alone. Jupiter has moons. Saturn has moons. Some are larger than small planets. Some hide oceans beneath ice. Some are shaped by tides powerful enough to keep their interiors active. Now move that architecture into the temperate zone of the nearest sun-like star. Suddenly the question is no longer only, did Webb see a giant planet? It becomes, what kind of system could exist around it? We cannot answer that yet. We do not know whether S1 has rings. We do not know whether it has moons. We do not even know whether S1 is truly a planet. But if it returns, the next challenge will be much bigger than recovering 1 point of infrared light. We will want to know what that light is actually telling us about the world itself. Because temperature, radius, clouds, composition, and age can all hide inside a few photons. And the next step is to pull those clues apart. If S1 returns, the next surprise may be that seeing the planet is only the beginning. But a point of infrared light is not a photograph of a world in the way we normally imagine one. Webb cannot yet show us clouds rolling across S1. It cannot reveal rings, storms, continents, or moons. At Alpha Centauri's distance, even a planet larger than Jupiter would still be far smaller than a single resolved pixel. What Webb receives is blended light, a tiny amount of thermal radiation compressed into one unresolved source. And from that tiny signal, astronomers have to work backward. How warm is the object? How large might it be? How much light should a planet of that size release? Could something else produce the same brightness? This is where the investigation becomes less like photography and more like touching an object in a dark room with one fingertip. You know something is there. Now you have to infer its shape. The 2024 candidate was detected in the mid-infrared DOC, a region especially useful for cool planets because planets can radiate strongly there, while stars become less overwhelmingly dominant than they are in visible light DOC. That does not mean Alpha Centauri A becomes faint. It means the contrast becomes slightly less impossible. A sun-like star is thousands of degrees at its visible surface. A cool giant planet may sit only a few hundred degrees above absolute zero. In visible light, the star wins brutally. In thermal infrared, the planet begins to contribute more of its own light. Imagine 2 metal objects in a dark room. One has been heated until it glows white. The other is merely warm. Your eyes see almost nothing from the warm object. But point a thermal camera at both, and suddenly the second object becomes measurable. Webb is doing a cosmic version of that. The tentative S1 signal is consistent with a cool giant planet, possibly with a temperature around 225 Kelvin. That is about minus 48 degrees Celsius. Cold by human standards. But a planet does not need to be comfortable for us to detect it. It only needs to release enough infrared energy at the wavelengths Webb can measure. And here comes the first trap. Brightness does not tell you temperature by itself. A small hot object can release the same amount of light as a larger, cooler object if you do not know the radius. Then a single infrared measurement leaves multiple solutions open. This is why the estimated size of S1 is model dependent. Researchers can compare the observed brightness with models of giant planets of different temperatures, radii, ages, and atmospheric properties. Some combinations fit, others do not. But models are not photographs. They are controlled guesses built from physics. The signal therefore points toward a planet-sized object without giving us a perfect physical portrait. Mass is even harder. A planet can be large without being extremely massive. Saturn is the obvious example. It is almost as wide as Jupiter, yet its mass is only about 1/3 as large. Their outer dimensions look similar, while the amount of material packed inside differs enormously. So if S1 has roughly Jupiter-like dimensions, that does not automatically make it a Jupiter-mass planet. The system's age matters too. Young giant planets can glow strongly because they are still releasing heat left over from formation. Older planets cool and fade. Alpha Centauri is not a newborn system, so a candidate giant there would be relatively mature. Its glow would need to make sense for an older world, rather than a newly formed furnace. That makes the detection more impressive. Webb is not being asked to find a blazing infant planet in a distant young system. It is trying to see a cold, mature object beside one of the brightest nearby, sun-like stars. Most directly imaged exoplanets discovered so far have been easier targets in one crucial way. They tend to be young, hot, massive, and far from their stars. Think giant worlds glowing like embers at the edge of a campfire. S1, if real, would be different. It would be cooler, older, closer to its star, and much more like the kind of architecture we actually see in our own solar system, where giant planets are not newborn fireballs sitting hundreds of astronomical units away. That is why this one faint source matters beyond Alpha Centauri. It tests whether Webb can push direct imaging toward ordinary planetary systems. But the light itself could still contain surprises. A planet's atmosphere changes the radiation escaping from below. Molecules absorb some wavelengths and allow others through. Clouds can trap heat, reflect radiation, or hide deeper layers. Chemical composition can reshape the spectrum. Right now, the candidate signal is far too limited to give us a rich atmospheric fingerprint. We should not imagine Webb already reading methane, water vapor, or ammonia from S1. It is not. First, the object must be recovered. Then astronomers need more measurements. But if repeated detections become possible, different infrared wavelengths could begin separating competing explanations for its temperature and atmosphere. A single point becomes several points on a spectrum. Several points begin forming a curve, and that curve can tell us what kind of object is glowing. There is another possibility astronomers have to guard against. Not every warm infrared source beside a star is a planet. Dust can glow. Debris can glow. Structures inside a planetary system can sometimes produce localized brightness that looks compact when the telescope cannot fully resolve it. Alpha Centauri A does not give scientists the luxury of assuming the most exciting answer. A candidate planet has to survive every boring explanation first. Dust structures tied to a disk behave differently from a compact body following a Keplerian orbit. A distant background object will not trace the same path around Alpha Centauri A. A detector artifact cannot keep appearing at positions predicted by gravity. If S1 comes back where an orbit says it should, the case changes immediately. Not because one more dot is beautiful, because the dots begin obeying a law. Gravity turns separate images into one physical object. And once an orbit emerges, mass may eventually become easier to constrain. A sufficiently massive planet tugs on its star. The motion is tiny, but precision radial velocity measurements can search for the star moving toward and away from us as the planet pulls it around their shared center of mass. For a close, bright star like Alpha Centauri A, astronomers have already spent years searching for subtle signals of companions. The binary star itself complicates that work. Stellar activity complicates it. Instrument precision complicates it. But direct imaging offers something those methods usually do not: the planet's position on the sky. Combine positional information with the star's motion and, in principle, the uncertainty starts shrinking. You move from "there may be something there" to an orbit, a mass, a temperature, and perhaps eventually an atmosphere. But Alpha Centauri offers one more advantage that is almost easy to overlook. It is close enough that every astronomical unit spreads farther across our sky than it would around a more distant star. That gives telescopes more room to separate planet from star. For direct imaging, it is practically next door. And if Webb can recover S1, the nearest Sun-like stellar system may become the laboratory where we learn how to photograph much smaller and colder worlds. Because beyond this possible giant planet lies the question that has followed Alpha Centauri for decades. If a Saturn-like world can hide there, what else could be hiding closer to the star? If a Saturn-like planet really is orbiting Alpha Centauri A, it may not be the most interesting world in the system. It may simply be the easiest one to see. That distinction matters, because telescopes do not show us everything that exists. They show us whatever happens to fit inside the narrow window created by wavelength, contrast, distance, orbit, and instrument sensitivity. A giant planet is large. It has a broad atmosphere. It can radiate enough heat for Webb's mid-infrared instrument to notice. An Earth-sized planet is a different problem. Shrink S1 from roughly Jupiter scale down to the width of Earth, and the amount of thermal radiation reaching Webb collapses. Move that smaller world closer to Alpha Centauri A, and it also sinks deeper into the star's glare. The planet could be there. The telescope could still miss it. This is one of the most important ideas in the Alpha Centauri story. A non-detection does not mean an empty system. Long before Webb made the 2024 observation, researchers modelled what its MIRI coronagraph might be able to see around Alpha Centauri A. Their calculations suggested that the favourable 1 to 3 astronomical unit region could reveal mature planets several times larger than Earth, while multiple visits might push sensitivity somewhat lower. But an actual Earth twin would remain beyond Webb's practical reach in this observing mode. In other words, Webb is opening a door. It is not yet walking through the entire house. Imagine Alpha Centauri A as a bright lamp surrounded by objects of different sizes. A beach ball may cast enough infrared glow to emerge from the glare. A baseball becomes harder. A marble may disappear completely. The marble can still be there. And around a star so close to us, that hidden marble is the object everyone wants. Alpha Centauri A is a solar-type star, our nearest close analogue to the Sun. Its neighbourhood is therefore one of the most tempting places to search for a rocky planet receiving an Earth-like amount of stellar energy. Future planet imaging missions are being designed specifically to attack this class of target, small worlds near bright nearby stars, not merely giant planets glowing strongly in infrared light. But the word Earth-like can become dangerous if we let it carry too much meaning. A planet can be Earth-sized and still be nothing like Earth. It might have a crushing atmosphere, no atmosphere, a global ocean, a global desert, permanent cloud cover, a surface sterilized by chemistry we have never experienced. Size is only the first clue. Orbit is another. Atmosphere is another. And habitability is a much harder question than simply drawing a green band around a star. The habitable zone only marks the range where liquid water could exist on the surface of a suitable planet under suitable atmospheric conditions. It is not a guarantee that water is present, or that biology ever began. Still, Alpha Centauri A gives us an unusually compelling laboratory. Models of the binary system indicate that planets can remain dynamically stable around Alpha Centauri A inside roughly 3 astronomical units. Simulations also show that rocky planets could plausibly survive there, despite the gravitational influence of Alpha Centauri B. So the companion star does not automatically destroy the possibility of terrestrial worlds. It simply changes the rules of the arena. Picture a small rocky planet orbiting Alpha Centauri A. From its surface, the main star would dominate the sky much as our Sun does from Earth. But Alpha Centauri B would also be present, a second star changing position over the decades as the binary pair move through their long orbit. It would not necessarily create the science fiction scene of two giant suns rising side by side every morning. The geometry would change. The brightness would change. But another star would be part of that world's sky. And beneath it, a planet could complete orbit after orbit while remaining completely invisible to Webb. That possibility is why S1 matters even if S1 itself is a gas giant. A giant planet can act like a signpost. It tells us that planet formation succeeded. It tells us that substantial material once existed in the disk around Alpha Centauri A. It gives us a real architecture to test instead of an empty theoretical system. But we should be careful here. One giant planet does not prove smaller planets exist. Planetary systems can be chaotic. Migration can move giant worlds inward or outward. Gravitational encounters can remove smaller bodies. The binary companion can reshape the disk from which planets form. The system we imagine may be nothing like ours. That uncertainty is part of the excitement. Because the solar system gave humanity one example of how planets can arrange themselves, exoplanets have spent the last 3 decades destroying the idea that this example is typical. We have found giant planets roasting beside their stars, planets packed into orbits tighter than Mercury's, worlds with densities like foam, worlds so hot that metals can exist as vapor. Nature does not build planetary systems from one blueprint. Alpha Centauri A could surprise us too. And the Webb candidate, if confirmed, would immediately force new questions about how that architecture formed inside a binary environment. Was the giant born near its present orbit? Did it migrate? Did smaller rocky planets form inside it? Could another giant exist farther out but remain undetected? Could belts of dust or debris occupy the gaps? Each answer changes where we should search next. This is where future telescopes become important. NASA is developing the Habitable Worlds Observatory concept around the ability to directly image Earth-like planets around Sun-like stars and study their atmospheres. NASA currently describes the mission as aiming for launch in the 2040s, with technologies focused on suppressing starlight deeply enough to expose extraordinarily faint nearby worlds. And Alpha Centauri would be an extraordinary target. A 2026 study examining future Earth-like planet searches noted that an Earth analogue around Alpha Centauri would deliver more photons to the planned Habitable Worlds Observatory than an Earth-like planet around any more distant system, simply because Alpha Centauri is so close. That is the advantage of living next door. A planet does not become brighter in itself. We just lose fewer of its photons across space. 4 light-years is still a distance almost impossible to feel. Light that reaches us tonight left the Alpha Centauri system more than 4 years ago. A spacecraft using today's conventional propulsion would face a journey measured not in years, but in millennia. Yet for astronomy, Alpha Centauri is close enough to transform what is possible. Every improvement in contrast matters more. Every tiny angular separation becomes easier than it would around a similar star 10 or 20 times farther away. Every photon becomes precious. So Webb's candidate may represent something larger than one possible planet. It may be the first rough outline of a planetary system we will spend generations resolving. First a warm dot, then an orbit, then perhaps other dots, then spectra, then atmospheres, and someday, perhaps, a pale rocky point buried far closer to Alpha Centauri A than S1 ever was. But before we imagine that world, there is another clue already hiding in this system. Because S1 may not have appeared for the first time in 2024, 5 years earlier, another telescope saw something near Alpha Centauri A. And if those two signals belong to the same object, the disappearing planet suddenly has a much longer history. 5 years before Webb saw S1, Another telescope had already found something strange near Alpha Centauri A. It was not James Webb. It was the Very Large Telescope in Chile, using an experiment called NEAR, New Earths in the Alpha Centauri region. During a campaign in 2019, astronomers spent roughly 100 hours pushing thermal infrared imaging toward a target that ground-based telescopes had rarely been able to approach, the habitable zone around the nearest Sun-like star. The result was not a confirmed planet. It was a weak, stubborn feature they named Candidate 1, or C1. C1 appeared about 0.85 arcseconds from Alpha Centauri A, corresponding to a projected separation of roughly 1.1 astronomical units. Its signal-to-noise ratio was only around 3, far below the kind of detection that lets astronomers celebrate without hesitation. But it appeared in multiple independent subsets of the data, and older images helped rule out an ordinary background object at that position. The team could not explain it with any known instrumental artifact. So C1 entered the scientific record in an awkward state. Possible planet. Possible warm dust. Possible unknown systematic. Nothing more. If it were a planet, its infrared brightness could be consistent with a world several times Earth's radius, somewhere in the broad Neptune to Saturn size range. But the same light could also come from a concentrated structure of warm exozodiacal dust, material analogous to the dust that fills the inner solar system and produces zodiacal light in our own night sky. The original MIRI study estimated that a dust structure tens of times brighter than our zodiacal cloud could mimic the signal. That ambiguity mattered. A planet is compact. Dust is spread out. But when the object you are trying to resolve is tiny, faint, and buried beside a star, the telescope can blur very different physical structures into something that looks frustratingly similar. C1 needed another observation. It never got a decisive one. Then 5 years passed, and Webb saw S1 on the other side of Alpha Centauri A. This is where the story changes. C1 and S1 were not found in the same place. In June 2019, C1 was southwest of the star. In August 2024, S1 appeared mostly east of it, at a larger projected separation of about 1.5 arcseconds, or roughly 2 astronomical units. If these were static background sources, the mismatch would be a problem. But planets move, and over 5 years, a planet with an orbital period of only a few years can circle its star more than once. So the researchers asked a dangerous question. What if C1 and S1 are the same object? Not 2 candidates. One world, seen twice. They took the measured positions from 2019 and 2024 and searched for orbits that could connect them while remaining dynamically stable around Alpha Centauri A. The result was not one clean orbit, but several families of possible solutions. Many had orbital periods between about 2 and 3 years. That means the candidate could have completed roughly 1.5 or 2.5 full revolutions between the NEAR observation and Webb's detection. Now picture what that means physically. In 2019, you catch a moving object near one side of a lamp. You lose it. More than 5 years later, another camera catches an object on the opposite side. There are many paths a real orbit could have taken between those 2 snapshots. Most are wrong. Some crash into unstable configurations. Some place the object where later images should have seen it. Others fit both detections and also hide the object during Webb's failed follow-ups. The researchers tested those possibilities. And this is the number that keeps the candidate alive. Among the dynamically stable orbits that fit both C1 and S1, about 52% were also consistent with the object being missed in both the February and April 2025 Webb observations because orbital motion carried it into regions of poor sensitivity. That does not mean there is a 52% chance the planet is real. Those are not the same statement. The calculation begins by assuming that C1 and S1 belong to the same orbit. Then it asks how often the later non-detections would make sense. The answer is that disappearing twice is not especially unlikely under those allowed orbital solutions. This is a subtle but crucial distinction. Science is not saying, "We are 52% sure we found a planet." It is saying, if these two signals are one planet, the later disappearances are compatible with many plausible orbits. That keeps the door open. The orbital solutions themselves are interesting. The candidate paths tend to be moderately eccentric, around an eccentricity of 0.4, meaning the orbit may be noticeably stretched rather than nearly circular. They also appear significantly tilted relative to the orbital plane of Alpha Centauri A and B. Some solutions move in a prograde direction with a mutual inclination near 50 degrees. Others are retrograde, tilted by roughly 130 degrees. If confirmed, that geometry would immediately become part of the mystery. Planetary systems often remember the flat disk from which they formed. Our major planets orbit the Sun in roughly the same plane. A strongly tilted giant around Alpha Centauri A could point toward a more complicated history, one shaped by migration, gravitational interactions, or the presence of the companion star. But again, we are standing on candidate evidence. The orbit is not measured, it is reconstructed from possibilities, and the two original signals do not even imply exactly the same kind of object on their own. C1's 2019 brightness, measured at shorter mid-infrared wavelengths, was originally interpreted as potentially coming from a smaller, warmer planet or from dust. S1, measured by Webb at 15.5 micrometers, is better matched by models of a much larger and colder giant, roughly Jupiter-sized and around 225 Kelvin. The 2025 analysis showed that one physical planet could potentially accommodate the combined constraints, with an estimated mass in the broad range of about 90 to 150 Earth masses. That is roughly Saturn territory. And suddenly the old C1 detection looks different. In 2021, it was a lonely 3 sigma feature that demanded an independent experiment. In 2024, an independent space telescope found another candidate near the same star. Neither observation proves the other, but together they create a path that gravity can test. That is the beautiful thing about orbital motion. Time becomes part of the instrument. Every month that passes moves a real planet somewhere predictable. Full structures do not have that freedom. Dust evolves differently. Instrument artifacts do not circle a star according to Kepler's laws. Background objects do not repeatedly land where a bound orbit says they should. So the next successful detection would do far more than add another point. It could connect 2019, 2024, and a future image into one moving world. 3 separated moments, one orbit, and if that happens, astronomers will finally be able to ask the question that neither NIR nor Webb can answer from a single detection. How massive is this planet really? And what has its gravity been doing to the rest of the Alpha Centauri system? If S1 is really a Saturn-class planet, then it cannot hide completely. Light can disappear behind a coronagraph. Gravity cannot. Every planet pulls on its star. The star does not remain perfectly fixed while the planet travels around it. Both bodies orbit a shared center of mass. And for a giant planet moving only a few astronomical units from Alpha Centauri A, that reflex motion should leave a measurable signature in principle. This is why S1 has to survive more than an imaging test. It also has to survive everything astronomers already know about the motion of Alpha Centauri A. Precision radial velocity observations have been watching this star for years. That method does not photograph a planet. Instead, it looks for tiny shifts in the star's spectrum as the star moves toward us and away from us under the pull of an unseen companion. Existing radial velocity limits already restrict how massive a planet with a period shorter than about 1,000 days could be around Alpha Centauri A. The Webb team notes that the inferred S1 mass range, roughly 90 to 150 Earth masses, can still fit those limits because radial velocity measures only the component of the motion projected along our line of sight. That is an important clue. S1 is not obviously too massive to have escaped earlier searches, but it may be heavy enough that those searches can eventually help confirm or reject it. Imagine a child holding an adult's hand and running in a circle. The adult barely moves, but not quite. Now shrink that motion to a star more massive than the Sun. Place the pair 4.3 light-years away and try to measure the wobble from Earth while another star is also orbiting nearby. That is the Alpha Centauri problem. The giant binary motion dominates the scene. Alpha Centauri A and B travel around each other on an eccentric orbit lasting almost 80 years. So the velocity of A is already changing because of a stellar companion vastly more massive than any planet. A planetary signal must be extracted from underneath that much larger motion, along with stellar activity and instrumental noise. The planet, if present, is a whisper inside a moving engine. Still, the whisper has a shape. A Saturn-class body on an orbit of a few years should produce a repeating velocity pattern. The exact amplitude depends on the planet's true mass, orbital period, eccentricity and, crucially, the tilt of the orbit toward us. If the orbit is close to face-on, direct imaging can show substantial movement across the sky, while radial velocity sees only a small back-and-forth motion. If the orbit is more edge-on, the velocity signal becomes stronger. This is where the possible geometry of S1 becomes useful. The combined C1 and S1 orbital solutions favor paths that are significantly inclined relative to the Alpha Centauri AB binary plane, with families near about 50 degrees or about 130 degrees of mutual inclination and an eccentricity around 0.4. The same analysis finds possible periods of roughly 2 to 3 years. Those are not final orbital elements. They are allowed solutions. But allowed solutions can make predictions. At a given future date, each possible orbit places the planet in a different patch of sky and gives Alpha Centauri A a slightly different expected velocity. New images eliminate paths that put the planet in the wrong place. New velocity measurements eliminate paths that demand a stellar wobble that is not there. The two methods attack the uncertainty from different directions. Direct imaging tells you where the planet appears beside the star. Radial velocity tells you how strongly the planet is pulling the star along our line of sight. Together, they can reveal something neither method knows cleanly by itself: the planet's true mass. And true mass matters. A 90 Earth mass world and a 150 Earth mass world may have similar apparent radii, yet they represent very different interiors. One could be a lower density giant with a huge envelope. The other could pack much more material beneath an atmosphere of similar visible size. Without mass, a glowing dot gives us only part of the world. Gravity supplies the missing scale. But the most interesting gravitational consequence may not be the star's wobble. It may be what S1 does to other planets. Studies conducted before the Webb candidate showed that planets can remain stable around Alpha Centauri A inside roughly 3 astronomical units, while the companion star imposes forced eccentricities and makes tightly packed systems harder to maintain than comparable systems around isolated stars. Simulations have even found configurations containing several Earth-mass planets that can survive for billions of years, provided their spacing and orbital phases are favorable. Now insert a Saturn-mass planet into that picture. The architecture changes. A giant planet does not politely occupy one lane. Its gravity reaches across surrounding space. Nearby small worlds can have their eccentricities increased. Resonances can open regions of instability. Certain orbits can be protected, while others are slowly pumped until they cross neighboring paths or are rejected. So if S1 is confirmed, one of the next questions will be brutally practical. Where can an Earth-sized planet still survive? That is not the same as asking where liquid water could exist. A habitable zone drawn from starlight means little if the orbit itself cannot remain calm for geological time. A rocky planet needs room. It needs an orbit that does not repeatedly swing too close to a giant neighbor. It needs to survive the pull of Alpha Centauri B, and it may need to avoid resonances that only become obvious after millions or billions of simulated years. This makes S1 a possible map maker, Its mass and orbit would define gravitational boundaries for every future planet search around Alpha Centauri A. If the giant stays mostly outside the central habitable region, interior rocky worlds might still have stable territory. If its eccentric path sweeps deeply inward, the available safe zones could shrink. If the orbit is strongly tilted, its long-term interactions with other planets could become more complicated still. We cannot choose between those outcomes yet. The current data are too sparse. But notice how the question has changed. At first, we asked whether one faint infrared point was real. Now that point is potentially telling us where unseen planets can and cannot exist. This is how planetary systems are reconstructed. Not by finding every world at once. By finding one body, measuring its gravity, then using that gravity to understand the empty spaces around it. Our own solar system works the same way. Jupiter's influence helped sculpt the asteroid belt, controls families of resonances, redirects small bodies, and leaves gravitational fingerprints across enormous distances. A giant around Alpha Centauri A would become a similar organizing force. And that creates a final twist. If S1 exists, perhaps the absence of other detections around Alpha Centauri A is not surprising at all. The smaller worlds may be exactly where our instruments are weakest, closer to the star, colder in contrast, and buried under light. We might already be looking at the system from the outside inward. First the giant, then the gaps its gravity creates. And only later, with a new generation of telescopes, whatever rocky worlds survived between them. But before we can use S1 as a gravitational map, Webb has to solve a more immediate problem. It has to know when to look again. Because an orbit that hides a planet can also tell us when the planet should come back out. The orbit that can hide S1 also gives astronomers something precious. A date. When the team combined the 2019 C1 position, the August 2024 S1 detection, and the two Webb non-detections from early 2025, they did not get one perfect orbital line. They got a swarm of possible paths. Each path sends the candidate through a slightly different piece of sky, but many of those paths begin bunching together again during one especially useful window. August 2026. In the published orbital analysis, that month stands out as an excellent opportunity to recover S1. For many of the stable C1 plus S1 solutions, the candidate should be more than about 1 arc-second from Alpha Centauri A and positioned away from the transition boundaries of Webb's 4-quadrant phase-mass coronagraph. That sounds like a tiny geometric detail. It is not. 1 arc-second is an angle so small that you could hide it behind the width of something microscopic held at arm's length. Yet for Webb, moving a possible planet from 0.7 arc-seconds to more than 1 arc-second from its star can change the observation from nearly hopeless to much cleaner. Because the coronagraph does not create a perfectly black circle around Alpha Centauri A, its sensitivity is shape. Imagine placing 4 dark glass panels over a floodlight, with narrow seams crossing through the center. A firefly moving around the lamp may be easy to see in one patch and almost impossible to see near a seam. The firefly has not changed brightness. The observing geometry has. MIRI's 4-quadrant phase mask works through interference rather than simply covering the star with an opaque disk. That allows powerful starlight suppression, but it also creates regions where sensitivity is worse. The 2025 analysis found that orbital motion could naturally have carried S1 into such difficult regions during the February and April follow-ups. So astronomers can turn the failure into a prediction. If the object is moving on one of the allowed orbits, it should not remain hidden forever. This is the heart of the test. A detector artifact has no orbit. A random subtraction residual has no reason to emerge at a position predicted from observations separated by years. A real planet does. The next useful sighting therefore needs to do more than produce another faint dot. Its location has to make sense relative to C1, S1, and the places where Webb saw nothing. Suppose a new image finds a compact source exactly where a large fraction of the orbital models place it. Suddenly, the August 2024 point gains a direction of travel. The 2019 C1 signal may gain a connection. The 2025 blank images become constraints rather than failures. And the invisible curve around Alpha Centauri A begins to close. That is why timing direct imaging observations is so different from simply taking more photographs. If you photograph a mountain, tomorrow usually gives you the same mountain. Photograph a short period planet, and tomorrow gives you a slightly different geometry. Wait months, and the change can be enormous. S1's candidate orbit may last only around 2 to 3 years on a human calendar. That is fast. Earth takes 1 year to circle the Sun. Jupiter almost 12, Saturn almost 30. A planet moving around Alpha Centauri A on a 2 to 3 year path can sweep through large orbital angles between observing seasons. The 2 to 3 year period comes directly from the allowed C1 plus S1 orbital families. And Webb cannot point at every target whenever astronomers want. The observatory circles the Sun in a halo orbit around the Sun-Earth L2 region, while its giant sun shield must keep the Sun, Earth, and Moon on the protected side of the telescope. Those thermal and pointing requirements create limited visibility windows for different parts of the sky. The planet moves. The star moves. The telescope has pointing constraints. The coronagraph has sensitive and insensitive regions. And Alpha Centauri B throws additional light into the problem. All of those clocks have to line up. This turns observation planning into something like trying to photograph a runner through a narrow opening in a moving fence while someone shines a spotlight into your camera. You do not only need a powerful camera, you need the runner to reach the opening at the right moment. There is another clock now counting down around Alpha Centauri A. A known background star, labelled KS5 in the analysis, is approaching Alpha Centauri A on our sky. The researchers calculate that between roughly mid-2027 and mid-2028, Alpha Centauri A and KS5 will pass within about 3 arcseconds of one another. That will make an already crowded high-contrast imaging problem even more complicated. So the recovery window matters for 2 reasons. The candidate may be moving outward into a more favourable part of Webb's field, and the background around the primary star is about to become less clean. But there is an important condition buried inside the prediction. The strong August 2026 forecast depends on treating C1 and S1 as the same object. If they are unrelated, then S1 has only one measured position from Webb. With 1 point, the family of possible orbits becomes vastly broader, and predicting where the object should be at any given date becomes much harder. The researchers explicitly warn that S1's position is far less constrained if it is unrelated to C1. This gives the next observation enormous leverage. Find S1 where the combined orbit predicts, and the old 2019 signal becomes much more interesting. Find nothing in a region where Webb should have been sensitive, and a large chunk of those orbital solutions disappears. Find a source somewhere completely unexpected, and astronomers may have to reconsider whether C1 and S1 are related at all. Every outcome teaches us something. That is what makes this a good scientific test. There is no result that needs to be protected. The candidate either keeps behaving like an orbiting planet, or the planetary interpretation begins to collapse. And even if the next observation recovers S1, confirmation will not end the story. Another position improves the orbit, but the physical nature of the source would still need scrutiny. Astronomers would want additional wavelengths. The published study points to Webb's NICAM as one possible way to distinguish atmospheric models, because different cloud and temperature structures predict different brightness between roughly 4 and 5 micrometers. Other observatories could eventually join the pursuit. The same study identifies possible follow-up routes involving visible light coronagraphy, future extremely large ground-based telescopes, radial velocity, and precision astrometry. Each method would attack a different piece of the candidate's identity. Thermal glow, reflected starlight, orbital movement, stellar wobble, possibly, one day, atmospheric features. But all of those possibilities depend on the simplest requirement first. The dot has to come back. and there is something almost poetic about the timing. The original analysis was published in 2025 and pointed directly toward August 2026 as a particularly favourable recovery opportunity. That window was not chosen because it sounded convenient. It fell out of the candidate's possible motion. Gravity made the appointment. Now the telescope has to see whether anything shows up. Because if a warm point appears where those orbital paths predict, we will no longer be talking about a mysterious light beside Alpha Centauri A in quite the same way. We will be watching a neighbouring world move. And once you can watch a planet move, the next question becomes irresistible. Could anything be moving around the planet itself? If S1 really is a giant planet, then the most Earth-like place in its neighbourhood may not be the planet at all. It could be something circling it. A moon? That idea sounds like a jump into science fiction. So we need to separate what Webb has actually measured from what gravity merely allows. S1 is still a candidate. The 2025 analysis placed it in the broad Saturn-mass range, with a radius around Jupiter's and a temperature near 225 Kelvin. But the object has not yet been confirmed as a planet. The same orbital study highlighted August 2026 as a favourable recovery window. The public, NASA, ESA, and archive material I could verify as of August 15, 2026 still describes S1 as a candidate rather than a confirmed recovery. But hypothetical does not mean meaningless. In our solar system, giant planets are surrounded by miniature systems of their own. Saturn alone carries moons ranging from tiny bodies to Titan, which is larger than Mercury, while Enceladus hides a global ocean beneath ice. If S1 formed with satellites, then the habitability conversation changes immediately. A Saturn-like planet is almost certainly not a place where you stand beside an ocean. Gas giants do not have ordinary hard surfaces. Descend into one and the atmosphere simply becomes denser, hotter, and more compressed. A sufficiently large rocky moon would be different. It could have ground an atmosphere, ice, possibly water. But being located inside a star's habitable zone would not automatically make that moon habitable. A moon around a giant planet lives inside two gravitational environments at once, and it receives energy from more than one source. Research on exomoon climates shows that such a moon can absorb direct starlight, reflected light from its planet, infrared radiation from the planet, and heat generated inside itself by tidal flexing. It can also repeatedly pass through the planet's shadow. So imagine standing on that moon. Alpha Centauri A rises. Its light warms the surface. Then the giant planet hangs above the horizon, enormous compared with our moon, reflecting some of that same starlight back toward you. Later, your orbit carries you behind the planet. The star disappears. For a while, day becomes eclipse. And beneath your feet, gravity may be kneading the moon's interior. That last effect can be gentle or catastrophic. A moon does not travel around its planet in perfect isolation. If its orbit is even slightly eccentric, the planet's gravitational pull varies as the moon moves closer and farther away. The body flexes. Mechanical energy becomes internal heat. We see an extreme version at Io, where repeated gravitational flexing by Jupiter and neighbouring moons generates tremendous internal heat and powers extraordinary volcanic activity. For a hypothetical exomoon, tidal heating creates a strange balance. Some internal heat could maintain geological activity or help keep water liquid beneath ice. Too much could push the surface toward a runaway greenhouse, making a world inside the stellar habitable zone far too hot. Researchers have therefore described a circumplanetary habitable edge, orbit too close to the giant planet, and tidal plus radiative heating can overwhelm otherwise favourable conditions. Distance from the planet matters almost as much as distance from the star. Too close, and tides can cook you. Too far, and the star can eventually pull you away. The outer gravitational boundary is related to the planet's Hill sphere, the region in which a moon can remain bound against the star's competing gravity. Its size depends on planetary mass and distance from the star. And S1 may not follow a gentle circular orbit. The combined C1 and S1 solutions include families with eccentricity around 0.4. If that approximate value survives future observations, S1's distance from Alpha Centauri A would change substantially during each revolution. That creates another rhythm. At eccentricity 0.4, the planet's farthest star distance is more than twice its closest distance. Because stellar illumination changes with the inverse square of distance, the amount of starlight reaching a moon could therefore vary by several times between those extremes. The system could breathe thermally. Bright, dim, bright again. A thick atmosphere or ocean might smooth some of those changes. A thin atmosphere might respond much faster. Models of hypothetical exomoons show that climate depends sensitively on orbital eccentricity, eclipses, tidal heating, and atmospheric heat redistribution. But we do not know S1's exact orbit. We do not know whether it has moons. And we certainly do not know whether any moon is rocky, large, wet, or atmospheric. This is where visual imagination has to stop and measurement has to begin. Even Alpha Centauri's closeness would not make an ordinary moon easy for Webb to separate from S1. Webb detected the candidate as an unresolved point at roughly 15.5 micrometers, about 2 astronomical units in projection from Alpha Centauri A. A normal satellite system would occupy a vastly smaller region around the planet and would remain blended with it at that resolution. So Webb would not simply photograph a little moon beside S1. Astronomers would have to search indirectly. A massive satellite could make the planet move around a planet-moon barycenter. Mutual eclipses could alter their combined light. Future instruments with finer angular resolution might attack the separation more directly. But every one of those searches comes later. First, is S1 real? Second, what is its orbit and mass? Third, does it possess satellites? Fourth, are any of those satellites massive and stable enough to matter? Only then does habitability become a serious question. That sequence may feel painfully cautious. It should. Alpha Centauri makes it unusually easy for our hopes to run ahead of the photons. It is our nearest Sun-like stellar neighbour. Put a possible giant planet in its temperate region, and the imagination instantly builds blue moons, clouds, oceans, even unfamiliar skies. Webb has not found any of those things. What it may have found is simpler and scientifically more useful. A cool giant whose conformation would demonstrate substantial planetary architecture around Alpha Centauri A. If that giant has moons, one candidate world becomes an entire hidden system. But another clue is already sitting inside the Webb observations, and it does not require us to invent a single moon. Webb searched not only for planets, it searched for dust. And what it failed to see around Alpha Centauri A may be almost as important as the point of light it did see. A planet is not the only thing that can glow around a star. Dust can glow too. Not the thick grey dust you wipe from a shelf, but microscopic grains spread through a planetary system, fragments released by collisions between asteroids, comets, and larger bodies. In our own solar system, sunlight scatters from this material to create the faint zodiacal glow visible from very dark skies. Around another star, the equivalent material is called exozodiacal dust, or simply exozodi. And for Alpha Centauri A, this dust matters for 2 completely different reasons. First, it can imitate a planet. Second, it can hide one. That is why the Webb team did not treat the August 2024 observation as a simple planet hunt. The MIRI campaign was designed to search the habitable zone region for both point-like planetary sources and extended thermal emission from dust. Across the 3 observing epochs, the team reached sensitivity to an exozodiacal cloud only about 5 to 8 times brighter than the solar system's own zodiacal cloud. They reported no significant extended dust emission at that level. That is an extraordinary kind of non-detection. Imagine turning off a stadium light and searching the field for one person carrying a candle. Now, add fog. Even if the person is there, the fog spreads light across the entire scene and makes the candle harder to isolate. Exozodiacal dust is the astronomical version of that fog. It does not have to form a smooth ring. Dust can be clumpy. Planets can trap grains in gravitational resonances, producing arcs, concentrations, and asymmetric structures. In direct images, those structures can create false planetary features or simply raise the background until a faint terrestrial world disappears into it. This was already part of the mystery surrounding C1. When the VLT-NIR experiment saw its candidate feature in 2019, the team could not rule out a warm dust structure as the explanation. The signal might have been a planet, but sufficiently concentrated exozodiacal emission could also have produced something similar. Webb pushed much deeper, and it did not reveal a bright habitable zone dust cloud. That does not automatically prove S1 is a planet. A compact dust feature could still be difficult to distinguish from a point source, and the Webb team explicitly kept the planetary interpretation at candidate status. But the lack of strong extended emission removes one of the simplest pictures. Alpha Centauri A does not appear to be surrounded by an overwhelmingly bright, warm dust disk that would obviously explain everything Webb saw. The scene appears cleaner, and that could matter enormously in the future. To understand why, place Earth at Alpha Centauri A. Do not change the planet. Only move our solar system next door. From 4 light years away, Earth would be a dim blue point almost buried beside a sun-like star. A future telescope would need to suppress the starlight and then collect the tiny remaining signal from the planet. But between the telescope and that planet lies dust. Every grain reflecting starlight adds photons that do not belong to Earth. Those photons create noise. At visible wavelengths, future exo-Earth imaging missions may find exozodiacal dust to be one of their largest astrophysical noise sources. A recent 2026 analysis also showed that even residual dust left after processing can distort extracted planetary spectra, weakening the apparent depth of molecular absorption features. So a relatively clean Alpha Centauri A system would be more than aesthetically pleasing. It could make future rocky planets easier to see. Think of trying to read a tiny road sign through a windshield at night. The sign is already faint. If the windshield is covered with illuminated mist, every extra reflection steals contrast. Clean the glass, and the sign does not become brighter. It simply becomes easier to separate from everything around it. That is what low exozodiacal dust could offer future telescopes. But the missing dust also tells us something about the system itself. Dust is temporary. Microscopic grains do not simply sit forever in stable orbits. Radiation, stellar wind, collisions, and gravitational interactions continually remove or redistribute them. For a mature planetary system to maintain a bright dust cloud, larger populations of asteroids or comets must keep grinding material down and replenishing it. Exozody therefore acts as a kind of visible smoke from ongoing small body activity. Webb did not find much smoke around Alpha Centauri A, but that does not mean there was never a fire. The star is old enough that the violent planet-building era would have ended billions of years ago. Planets could have formed, migrated, collided, and cleared much of their surrounding debris long before humans began looking. A mature system can contain major planets while carrying relatively little detectable water. Our own solar system is proof that planets and a faint zodiacal cloud can coexist. So we should resist a tempting mistake. No bright dust does not mean no asteroids. No bright dust does not mean no comets. And it certainly does not mean no planets. It means Webb found no exozodiacal disk brighter than roughly the measured 5 to 8 Zodi sensitivity in the region and geometry tested. That restraint matters because direct imaging lives on contrast. Every time astronomers subtract one contaminating source, another layer appears beneath it. First Alpha Centauri A itself, then Alpha Centauri B, then telescope diffraction, then detector structure, then background stars. then zodiacal emission from our own solar system, then possible dust around the target star. Only after all of that can one ask whether the faint remainder belongs to a planet. S1 survived enough of those layers to remain interesting, and the low dust limit makes the Alpha Centauri system an even more valuable target for the era after Webb. NASA studies of future direct imaging missions explicitly treat exozodiacal dust as an obstacle to finding Earth-like planets, because dust in a habitable zone can raise the background and complicate both detection and atmospheric characterization. Around Alpha Centauri A, we may have been given an unusually favorable laboratory. A nearby Sun-like star, a habitable zone spread widely enough across our sky to attack with high-contrast imaging. No detected bright, warm dust cloud at Webb's current limit, and perhaps a giant planet already moving through the system. Put those pieces together, and the emptiness in the Webb image starts becoming informative. The dark spaces may not be empty. They may simply be clean. And clean darkness is exactly what future telescopes need if they are ever going to find something smaller than S1. But there is another reason the dust matters. If S1 is real, its gravity may be partly responsible for shaping that clean environment, scattering debris, trapping material into resonances, or carving structures too faint for Webb to see. Which means the next clue may not come from the planet's light at all. It may come from the architecture of everything around it. If S1 is real, then its most important effect may not be the light we see from it. It may be the empty space around it. Planetary systems are not arranged like ornaments placed carefully on a shelf. They are sculpted by gravity. Massive planets tug on smaller bodies, trap debris into resonances, clear unstable regions, redirect comets, and sometimes eject entire worlds. Over millions and billions of years, those repeated interactions can turn a chaotic young disk into a structured system of planets, belts, gaps, and quiet zones. Our own solar system gives us a familiar example. Jupiter is not merely a large planet sitting beyond Mars. Its gravity helps shape the asteroid belt and creates resonant gaps where certain orbital periods become unstable. Saturn and the outer planets add their own patterns. The architecture we see today is partly a fossil record of gravitational interaction. If S1 really has a mass somewhere around 90 to 150 Earth masses, then Alpha Centauri A may contain its own powerful sculptor. If C1 and S1 are the same object, the allowed orbital families are moderately eccentric and significantly tilted relative to the binary plane. Those values are provisional, but they matter because a massive body on a stretched or tilted path can disturb a wider volume of space than one moving on a perfectly circular, flat orbit. Picture S1 moving around Alpha Centauri A. At one point in its orbit, it approaches the inner system, then it swings outward. Every passage gives nearby smaller bodies a gravitational nudge. One nudge is tiny. 1 billion nudges are architecture. Some locations would remain calm. Others could become dangerous because of mean motion resonances, where orbital periods fall into simple ratios. A small body that circles the star once for every 2 or 3 circuits of the giant can receive repeated pulls at nearly the same orbital phase. The effect is like pushing a child on a swing at exactly the right moment. Push once, almost nothing happens. Keep the rhythm, and the swing climbs higher. In a planetary system, that climbing motion can mean increasing eccentricity until an orbit crosses another planet's path or approaches the star too closely. Studies of Alpha Centauri A and B already show that the binary itself limits stable planetary real estate. Numerical simulations find that planets around either star can survive within roughly 3 astronomical units under favorable configurations, while the companion begins to destabilize more distant circumstellar orbits. Hydrodynamical work also finds that the planet-forming disks around A and B would have been truncated to roughly this compact scale. That makes S1 especially interesting. If a giant planet formed inside a disk only a few astronomical units wide, It consumed a meaningful fraction of the material and gravitational space available around Alpha Centauri A. A 2024 study estimated that such disks could still contain enough solid material to build rocky planets, so a giant planet would not necessarily prevent terrestrial worlds from forming, but it could strongly influence where they survive. The difference is crucial. Formation asks, could a rocky planet have been built? Stability asks, could it remain there for billions of years? A world can pass the first test and fail the second. Imagine an Earth-mass planet forming closer to Alpha Centauri A than S1. If their orbits are well separated, the rocky world might remain stable for geological time, but if S1's eccentric orbit reaches too far inward, or if the smaller planet sits inside a strong resonance, its orbit could slowly stretch. Not tonight. Not next century. Perhaps not for 1,000,000 years. But planetary habitability needs patience. An ocean world that remains temperate briefly and is then thrown into a wildly eccentric orbit is not the kind of long-lived environment astronomers usually mean when discussing stable habitability. This is why confirming S1's orbit matters almost as much as confirming S1 itself. Every new positional measurement would shrink the family of allowed paths. Once astronomers know its semi-major axis, eccentricity, inclination, and mass with useful precision, they can fill the surrounding space with hypothetical smaller planets in computer simulations. Then they let gravity run. 1,000,000 years. 100 million. 1 billion. Most simulated worlds either remain quiet or reveal where instability grows. The result becomes a map we cannot photograph directly. Safe lanes, resonant traps, chaotic borders, possible homes for rocky planets, and Alpha Centauri B adds a second layer to that map. It is not a decorative second sun. Its gravity changes the environment around A over the binary's nearly 80-year orbit. Long-term studies have found resonant structure at the stability boundaries, while highly inclined configurations can experience effects that trade orbital inclination for eccentricity. In simple language, the second star can slowly bend and stretch orbits. Add a giant planet, and those influences can overlap. This does not guarantee chaos. Stable configurations exist around Alpha Centauri A, and simulations show terrestrial planets can survive there for very long periods. But the exact locations depend on the system's architecture. S1, if confirmed, would become a major missing piece of that architecture. There is also a subtler possibility. A giant planet may help explain why Webb sees so little warm dust. Massive planets can scatter debris outward, eject small bodies, or trap material into resonant structures. We do not yet have evidence that S1 produced the low exozodiacal level measured by Webb. The system's age alone could account for much of the clearing. But if S1 is real, future dynamical models can test whether its orbit should create specific gaps or concentrations in the remaining material. Webb's existing observations place unusually deep limits on warm exozodiacal dust around Alpha Centauri A, reaching roughly 5 to 8 times the brightness of our own zodiacal cloud, without detecting significant extended emission. That would turn dust from noise into evidence. A faint ring at the right radius, an asymmetric clump, a cleared zone. Each could become a gravitational fingerprint. In many planetary systems, astronomers image a disk first and then ask whether unseen planets could explain gaps, spirals, warps, or rings. Around Alpha Centauri A, Webb may have given us the reverse. The dust is faint. The possible planet came first. So instead of using a disk to predict a planet, we may eventually use the planet to predict what little structure the disk should have. Then another telescope can search for it. That is the larger transformation happening here. S1 began as a faint point, surviving image subtraction. If it returns, it becomes an orbit. Measure the orbit, and it becomes a gravitational actor. Measure its mass, and it becomes an architect. Then every dark region around Alpha Centauri A becomes a question. with boundaries set by physics. Could an Earth-mass world survive here? Could an asteroid belt remain there? Could a moon system stay bound? Could another giant hide farther out? The empty space stops being empty. It becomes constrained. And once astronomers know where stable rocky worlds could hide, they can choose the instruments most capable of finding them. Because Webb is only one chapter in this search, the next generation will try something even harder. Instead of looking for a warm giant glowing in infrared light, it will try to separate a tiny rocky planet from the glare of a nearby sun. And Alpha Centauri A may be the best place in the sky to attempt it. The next telescope does not need S1 to be brighter. It needs Alpha Centauri A to become darker. That is the central problem behind the search for a rocky world around a nearby sun-like star. An Earth-sized planet in reflected visible light can be roughly 10 billion times fainter than its host star. The planet may sit only a tiny angle away from that star in our sky. To reveal it, a telescope must remove nearly all of the starlight while preserving the few photons arriving from the planet beside it. Webb was never built primarily for that task. Its Alpha Centauri experiment is powerful precisely because MIRI can search for thermal emission from a relatively large, cool planet. A smaller rocky world would release far less infrared light and would likely sit deeper inside the region where the star overwhelms the image. The next generation is being designed to push through that wall. NASA's Habitable Worlds Observatory, or HWO, is a developing flagship mission concept intended to directly image Earth-sized planets in the habitable zones of sun-like stars and then analyze their light for atmospheric chemistry. NASA describes the observatory as operating across ultraviolet, optical, and infrared wavelengths, with the search for potentially habitable planets as one of its defining goals. The engineering challenge begins with contrast. Imagine putting a tiny blue bead 1 centimeter from a stadium floodlight, then walking hundreds of kilometers away and trying to photograph the bead without allowing the floodlight to wash across your camera. You cannot simply make the detector more sensitive. A more sensitive detector records more unwanted starlight too. You have to control the light itself. One solution is a coronagraph. A high-performance coronagraph combines masks, carefully shaped optics, and extreme control of the telescope's wavefront to redirect or cancel the star's light, while allowing light from a nearby planet to survive. NASA is already developing vortex masks and deformable mirrors for the level of starlight suppression needed by future Earth imaging missions. Those deformable mirrors make microscopic corrections to optical imperfections so small that NASA describes the required control in terms approaching subatomic scale surface precision. The words sound technical. The physical idea is simple. Make a dark hole beside the star. Not a literal hole in space. A region in the telescope's image where destructive interference and wavefront correction reduce the stellar glare enough that a planet can emerge. NASA's Roman Space Telescope will help test important pieces of that technology before HWO. Its coronagraph instrument is designed as a technology demonstration for high-contrast imaging in space, including high-order wavefront sensing and control. NASA says those techniques are critical stepping stones toward directly imaging Earth-like planets with HWO. Roman is not simply a smaller version of the final mission. It is a rehearsal for precision. A real spacecraft flexes. Its temperature changes. Mirrors shift by tiny amounts. A pointing error that would be irrelevant for a normal image can pour starlight into the exact region where an Earth-like planet should be hiding. Future observatories therefore have to maintain darkness, not merely create it once. And Alpha Centauri adds another complication. There are 2 bright stars. A coronagraph, optimized to suppress Alpha Centauri A, may still receive contaminating light from Alpha Centauri B. NASA has supported technology specifically aimed at suppressing light in multi-star systems, using Alpha Centauri as a prime example of why a single-star solution is not always enough. So the nearest sunlight target is also one of the messiest. But distance gives something back. At roughly 4.3 light-years, Alpha Centauri is so close that a 1 astronomical unit orbit spreads across a relatively generous angle on our sky, compared with the same orbit around a star tens of light years away. The physical separation does not change. The apparent separation does. Hold 2 fingers apart. Now walk backward. They seem to squeeze together. Nearby planetary systems give telescopes the opposite advantage. Their planets appear farther from their stars in angular terms. That makes Alpha Centauri an unusually valuable proving ground for high-contrast imaging. Ground-based astronomy is preparing its own attack. ESO's extremely large telescope is designed with a primary mirror about 39 meters across, and its exoplanet program includes direct detection and atmospheric characterization. Its METIS instrument will work in thermal and mid-infrared wavelengths, with adaptive optics and high-contrast imaging. ESO has long identified Alpha Centauri as a particularly promising target for this capability. A mirror that large changes the geometry. Larger apertures produce finer angular resolution. In simple terms, the telescope can separate objects that appear closer together on the sky. That means future ground-based instruments may reach inward toward regions Webb struggles to resolve, especially around the very nearest stars. But Earth-like planet imaging from the ground faces an enemy Webb avoids. Our atmosphere. Air-shaped. Water vapor absorbs infrared light. Temperature differences create thermal background. The sky itself glows. Adaptive optics can measure atmospheric distortion and bend mirrors in real time to compensate, but the correction has to happen extraordinarily fast and accurately. Space removes that atmosphere. Ground observatories compensate with enormous collecting area. The 2 approaches are complementary. One may find a signal. Another may measure motion. A third may obtain a spectrum. And eventually, those pieces could converge on one tiny world. If a rocky planet is found around Alpha Centauri A, the first image will probably be profoundly disappointing to the eye. No continents, no clouds you can recognize, no blue marble. Just a point, perhaps only a handful of pixels after careful processing. But the point can contain a spectrum, split its light by wavelength, and molecules in an atmosphere may leave absorption patterns. HWO is being developed not merely to detect potentially Earth-like planets, but to characterize their atmospheres and search for combinations of chemistry that could inform assessments of habitability and possible life. NASA is currently advancing industry technology studies for that mission concept, which remains in development rather than being a launched or finalized observatory. That last distinction matters. No future telescope can promise life around Alpha Centauri. It cannot even promise an Earth. What engineers are trying to build is the ability to ask the question directly. Is there a small planet there? What does its atmosphere contain? Is water present? What gases coexist? Could ordinary geology explain them? Every answer would begin with suppressing a star until a speck beside it becomes measurable. And this is why S1 matters even before confirmation. A recovered giant planet would provide an orbital map of the system before the Earth-searching machines arrive. It would tell future observers where a massive body moves, which regions might remain dynamically stable, and where the glare from the giant itself could complicate observations. Webb may therefore be doing reconnaissance, not finding the final world, learning the terrain. First we identify the largest hidden architecture around Alpha Centauri A, then we push inward. Smaller, fainter, closer to the star, until the target is no longer a Saturn-like world glowing in thermal infrared, but something closer to the size of the planet beneath Earth. And if that day comes, one measurement will matter more than almost any other. Not whether the world looks blue, whether its atmosphere is chemically out of balance. Suppose a future telescope finally finds the object everyone hopes is hiding around Alpha Centauri A. Not a giant, a small rocky planet. It sits at a distance where liquid water could be possible. Its orbit is stable. its reflected light is separated from the star, and after years of engineering, astronomers collect enough photons to spread that tiny point into a spectrum. Then something strange appears. Oxygen. For a few seconds, that word alone would be enough to set the imagination on fire. On Earth, oxygen is intimately connected to life. Photosynthetic organisms continually release it, and today it makes up a large fraction of our atmosphere. Future observatories, such as NASA's developing Habitable Worlds Observatory, are being designed to search the atmospheres of directly imaged potentially habitable planets for gases including oxygen and methane. But oxygen is not a confession. A planet cannot simply show us one molecule and be declared alive. That is because planets have chemistry even when biology is absent. Ultraviolet light can break molecules apart. Hydrogen can escape to space. Water can be lost. Rocks can react with gases. Volcanoes can supply new material. Oceans can absorb it. Different stellar spectra can drive atmospheric chemistry down pathways that never occurred on modern Earth. Under some conditions, a lifeless planet can accumulate oxygen, and under other conditions, a living planet can hide it. That is the trap. Astrobiologists therefore do not treat a single atmospheric gas as a magic word. Oxygen becomes meaningful only in context. The star, the planet's climate, other gases, possible oceans, geological processes, and the chemical reactions that should be destroying or creating what we observe. Research on oxygen biosignatures explicitly warns that abiotic mechanisms can generate substantial atmospheric oxygen, while genuine biospheres can also produce false negatives if oxygen remains too scarce to detect. So imagine the spectrum again. This time, beside oxygen, we find methane. Now the situation becomes more interesting. On present-day Earth, oxygen and methane react. Left without continuous sources, they do not comfortably coexist at their observed levels. Life keeps replenishing both parts of this chemical tension. Photosynthesis supplies oxygen, while biological processes contribute much of Earth's methane. NASA uses this coexistence as an intuitive example of atmospheric disequilibrium, chemistry that appears to be continually pushed away from the state it would naturally settle into. Think of walking into an empty kitchen. One end of the room is covered in fresh ice. The other contains a roaring heater. If no one has been there for years, you expect those extremes to relax toward equilibrium. If they remain together, something must keep rebuilding the difference. Atmospheric disequilibrium works in a similar way. The exciting question is not simply, is methane present? It is. Why has this atmosphere not chemically erased the combination we see? That why is where biology may enter. But even oxygen plus methane would not allow astronomers to skip directly to aliens. Methane has non-biological sources. Water reacting with certain rocks can generate hydrogen and support abiotic methane production. Volcanism can contribute reduced gases. Impacts and interior chemistry can complicate the picture. Researchers therefore evaluate methane together with carbon dioxide, carbon monoxide, the planet's geological context, and the amount of methane that plausible non-biological mechanisms could sustain. The atmosphere becomes a crime scene. Every gas is evidence. None is the culprit by itself. And this is why a nearby rocky planet around Alpha Centauri A would be so valuable. Distance gives us photons. More photons mean better spectra. Better spectra mean that instead of detecting one broad feature, astronomers may be able to measure several atmospheric components and test whether they make sense together. Alpha Centauri's closeness does not guarantee an easy observation, but it makes any suitable terrestrial planet there an exceptionally bright direct imaging target compared with similar worlds farther away. We would want water vapor because it helps establish whether the atmosphere contains a major ingredient associated with surface habitability. We would want carbon dioxide because it affects climate and gives context for the planet's carbon cycle. We would want oxygen or ozone. We would want methane if it is abundant enough. And we would search for combinations, not trophies. NASA's current HWO concept reflects exactly that strategy. Its science case is built around directly imaging potentially habitable worlds and using spectroscopy to search for multiple indicators of habitability and possible biosignatures, rather than relying on one molecule alone. Even then, there is another problem. Earth itself would not always have passed our future life detection test. Life appeared on our planet long before the atmosphere became rich in oxygen. For enormous stretches of Earth history, a distant telescope could have looked directly at a living world and struggled to detect the familiar oxygen-methane combination we associate with the modern biosphere. Studies of Earth's atmospheric evolution show that oxygen or ozone could have been weak remote indicators for much of our planet's history, while methane could also have been difficult to detect during long intervals. That means silence is not proof of death. A rocky Alpha Centauri planet could contain oceans and biology, while showing us an atmosphere that looks frustratingly ordinary. Or it could present oxygen without life. The same telescope can face false positives and false negatives. This is why the eventual search will probably feel much less like a single discovery moment and much more like an investigation that keeps tightening. First, detect the planet. Measure its orbit. Estimate its radius. Search for an atmosphere. Measure several gases. Understand the star's ultraviolet radiation. Model oceans and surface temperatures. Look for geological explanations. Observe again and again. The strongest case for life would come when multiple independent observations become difficult to explain with one lifeless model. Not certainty from one spectral line. Convergence. That word may define the next era of astrobiology. And Alpha Centauri A offers a particularly powerful version of the experiment because we already know so much about the star and can continue watching the system for decades. If S1 is confirmed, we would also know more about the gravitational architecture surrounding any smaller world. The giant candidate would then become background context for a much quieter signal. A few reflected photons from stone, air, cloud, and perhaps ocean. From 4.3 light-years away, those photons would have left their planet years before reaching our instruments. We would not be seeing that world as it is tonight. We would be seeing its recent past. And if its spectrum ever showed a genuinely difficult-to-explain chemical imbalance, humanity would face a question unlike anything Webb's S1 candidate can answer. Not, is there another planet next door? But, is something on that planet actively changing its atmosphere? Before we reach that question, however, there is a more immediate reality to confront. Even if Alpha Centauri A hides an Earth, finding it does not mean we can go there. 4 light-years sounds close on a star map. For a spacecraft, it is an abyss. 4 light-years sounds close only because the universe is enormous. On a map of the Milky Way, Alpha Centauri is almost touching us. Alpha Centauri A and B lie about 4.37 light-years away, making them the nearest sun-like stars to our solar system. In ordinary distance, that is roughly 41 trillion kilometers. Light itself needs more than 4 years to cross it. Now slow down. Imagine Earth's orbit around the Sun as a circle only 1 centimeter across. At that scale, Alpha Centauri would not be sitting on the same desk. It would be kilometers away. That is the trick hidden inside the phrase, next door. Stars are neighbors only because almost everything else is much farther away. For spacecraft, the gap becomes brutal. Voyager 1 is humanity's most distant spacecraft and is escaping the Sun at about 17 kilometers per second. At that speed, if you could point a Voyager-like craft directly toward Alpha Centauri and somehow maintain the same velocity forever, a journey across 4.37 light-years would take roughly 77,000 years. Voyager 1 is not actually headed toward Alpha Centauri. The comparison simply translates the distance into a speed we have already achieved. 77,000 years. That is not a mission. That is a civilization problem. The spacecraft would need to remain functional through timescales longer than recorded human history by an enormous margin. Electronics would age, power systems would fail, dust grains would become hazards, navigation errors that looked microscopic near Earth could grow into gigantic misses after trillions of kilometers. And a crewed ship would multiply every problem. Food is the obvious one, but not the hardest. You would need energy, radiation shielding, repair systems, closed-loop water and air, medicine, spare parts, and a social system capable of surviving a journey whose destination no living passenger at launch might ever see. That is why serious concepts for reaching nearby stars usually begin by removing the crew. Make the spacecraft tiny. Make it fast. Accept a flyby. One of the best-known examples is Breakthrough Starshot, a research and engineering program built around light-driven nanocraft. Its proposed architecture uses powerful ground-based lasers to accelerate extremely small, sail-equipped probes toward roughly 20% of the speed of light. At that speed, a craft could cross the distance to Alpha Centauri in a little over 20 years, rather than tens of thousands. The program describes this as a proof-of-concept goal, not an existing transportation system. The difference is almost absurd. Voyager speed, tens of thousands of years. 1/5 light speed, about 2 decades. But gaining that speed creates new enemies. At 20% of light speed, you are moving about 60,000 kilometers every second. A grain of dust is no longer just dust. Relative velocity turns tiny particles into high-energy impactors. The sail and electronics must survive interstellar material for years while remaining extraordinarily light. The probe must navigate toward a target system that is itself moving. Then, after crossing trillions of kilometers, it must aim its instruments during a flyby that could pass in hours. There may be no second chance, and stopping is even harder. A laser can accelerate a sail while the spacecraft is near the solar system, because the energy source remains behind, but once the probe reaches Alpha Centauri, there is no matching giant laser waiting on the far side to break it. A fast flyby is therefore much easier than entering orbit. You could race through the system, collect images and measurements, and continue into interstellar darkness. That would still be extraordinary. But think about what we would want if S1 is confirmed. We would want to pass Alpha Centauri A. We would want to locate the giant. We would want to search for moons. We would want to scan inward for rocky worlds. We would want spectra, magnetic fields, dust, plasma, perhaps images of a planet that future telescopes had already identified from Earth. All of that would have to happen while the target flashes past at a significant fraction of light speed. A 20-year voyage could end in minutes of the most valuable science. And then comes the silence. Even if the probe works perfectly, communication must obey the same distance that created the journey. A message sent from Alpha Centauri takes about 4.37 years to reach Earth. If Earth immediately sent instructions back, those instructions would need another 4.37 years to arrive. A simple question and response cycle would span almost 9 years. There is no joystick, no real-time steering. The spacecraft has to become autonomous. It must recognize targets, decide which observations matter, recover from failures, compress data, point a transmitter toward a tiny distant solar system, and do all of this with severe power and mass limits. Communication may be as difficult as propulsion. A tiny probe can be accelerated more easily precisely because it is tiny, but a tiny transmitter is weak. A tiny power source stores little energy. A tiny antenna collects and directs less signal. The machine that is easiest to send becomes one of the hardest to hear. Researchers have proposed swarms partly to attack this problem. A 2024 NASA Innovative Advanced Concept Study explored gram-scale interstellar probes traveling together and coordinating communications. While assuming technology such as an enormous laser beamer and very large receiving systems on Earth, NASA described such laser-driven gram-scale probes as a possible route to another star this century, but the study remains conceptual. Other propulsion ideas exist. NASA studies have examined fusion, antimatter, photon sails, and beamed propulsion as possible routes toward practical interstellar flight. One NASA-backed concept, Proxima, explored a beamed propulsion architecture targeting about 10% of light speed and a roughly 42-year cruise to Proxima Centauri. These are research concepts, not vehicles sitting on launch pads. That distinction is important. We know physics allows objects to move between stars. Nature does it constantly. Comets can be ejected. Stars pass through the galaxy. Light crosses the gap in years. The problem is not whether Alpha Centauri can be reached in principle. The problem is building something useful that reaches it within a human lifetime and still works when it gets there. And this brings us back to Webb. A telescope sitting near Earth can study Alpha Centauri without crossing 4 light-years at all. Its photons do the travelling for us. The possible S1 signal left the system years before Webb collected it. We receive the light, measure it, reconstruct an orbit, estimate a temperature, and potentially map a planetary system while never leaving the solar system. For now, astronomy is our interstellar spacecraft. It is absurdly slow in one sense, because every image shows the past. But it is astonishingly efficient in another. We can investigate a world trillions of kilometers away simply by catching what arrives. That may remain the dominant way humanity studies Alpha Centauri for a long time. And yet, the moment we identify a confirmed planet there, especially a rocky one, the engineering question will stop feeling abstract. We will know exactly where we want to go. Then the challenge changes from finding a destination to surviving the road, and the road contains something that becomes far more dangerous as speed rises. The almost empty space between the stars. The space between the Sun and Alpha Centauri looks empty. At ordinary spacecraft speeds, that is mostly a blessing. At 20% of the speed of light, it becomes a weapons range. A Starshot-style probe would not cross a perfect vacuum. Interstellar space contains gas, mostly hydrogen and helium, along with heavier atoms, charged particles, cosmic rays, and microscopic dust grains. Voyager's measurements beyond the heliopause have already shown that the environment outside the Sun's protective bubble is filled with particles and cosmic radiation rather than true nothingness. The material is incredibly thin, but speed changes what thin means. Imagine driving through a light rain at walking pace. Each drop taps your face. Now imagine meeting the same drops at 60,000 kilometers per second. The rain has not become denser. The collision energy has changed. At about 0.2 times the speed of light, even individual atoms strike the front of a spacecraft with energies high enough to damage material. Studies of relativistic probes have found that repeated bombardment by interstellar gas can create tracks, implant hydrogen and helium inside solids, and eventually cause structural effects such as bubbling, blistering, and erosion. Dust grains are rarer, but each carries far more mass and can excavate craters or explosively vaporize material where it hits. This creates a strange reversal. For Voyager, interstellar gas is something to measure. For a relativistic probe, the same medium becomes something to survive. One detailed analysis of a 0.2c spacecraft estimated that gas bombardment could damage the surface of quartz to depths around 1/10 of a millimeter along an Alpha Centauri-class journey. In the same model, dust impacts could erode roughly 0.5 millimeter of exposed material under assumed interstellar conditions. 0.5 millimeter sounds trivial, until your entire spacecraft may be only millimeters thick. A gram-scale probe has almost no spare mass. Every shield competes with the camera, computer, communication system, power source, and sail. Add too much protection, and the laser can no longer accelerate the spacecraft to the intended speed. So the engineering problem becomes cruelly circular. To survive the journey, make the spacecraft heavier. To reach the required speed, make it lighter. Researchers studying starshot-like vehicles have explored narrow, elongated spacecraft geometries that minimize the frontal area exposed to impacts, along with protective layers placed on the forward edge. A 2023 analysis estimated millimeter-scale shielding for one set of gram-scale probe assumptions, with the protection taking a few % of total spacecraft mass. The exact requirement depends strongly on geometry, material, and the uncertain dust environment. And that last phrase matters. We do not have a perfect inventory of every grain between here and Alpha Centauri. The average medium can be modelled. One unusually large grain sitting in exactly the wrong place is much harder to plan around. Kinetic energy rises rapidly with velocity. A particle invisible to the naked eye can release enormous energy locally when it hits at relativistic speed. Larger grains are much rarer than tiny ones, but the mission crosses more than 40 trillion kilometers of space. A low probability repeated across an enormous path stops feeling comfortably low. You cannot steer around what you cannot see. Even detecting a dust grain far enough ahead to dodge it is difficult when the spacecraft covers roughly the Earth-Moon distance in only a few seconds. And changing course has a cost. Every maneuver consumes energy or demands some other mechanism for altering momentum. For a probe optimized down to grams, there may be little room for a conventional propulsion system capable of repeated evasive motion. So survival may depend more on shape and shielding than avoidance. Point the smallest possible cross-section forward. Put sacrificial material there. Hide delicate electronics behind it. Let the shield take the punishment for 20 years. But particles can do more than dig holes. They can charge the spacecraft. Collisions with interstellar particles and exposure to ultraviolet radiation can leave a fast probe electrically charged. Research on relativistic spacecraft has shown that interaction between that charge and interstellar magnetic fields could gradually deflect the vehicle's trajectory. The probe can also develop an uneven charge distribution, creating additional electromagnetic effects. At ordinary travel speeds, a tiny deflection may sound harmless. Across light years, tiny angles become gigantic distances. Imagine aiming at a coin 4 kilometers away. Now stretch that target distance to 40 trillion kilometers. A microscopic pointing error at launch can become a miss measured in millions of kilometers by arrival. Navigation is therefore not something the spacecraft completes when the laser turns off. It has to know where it is going, while the medium itself slowly perturbs the path. Then there is radiation. Once a spacecraft leaves the heliosphere, the protective influence of the solar wind fades and galactic cosmic rays become more prominent. Voyager detected this change directly. Heliospheric particles dropped, while cosmic rays from outside the heliosphere increased after the spacecraft crossed into interstellar space. A tiny electronic probe does not fear radiation sickness. Its circuits do. High-energy particles can alter bits in memory, damage detectors, degrade electronics, and accumulate material damage over years. Redundancy helps. Radiation-hardened electronics help. Error-correcting software helps. But once again, every backup system costs mass. A human interstellar vehicle would face the same environment on a far more severe scale. A crew requires thick protection not just for electronics, but for living tissue. The spacecraft would have to shield passengers from decades of cosmic radiation, while also surviving high-speed impacts from the direction of travel. At relativistic speed, the front of the ship becomes the dangerous direction. Everything ahead is blue-shifted and energized by motion. The emptiness becomes a stream. This is why the fastest proposed interstellar missions often start with machines rather than people. A gram-scale probe can accept damage margins no human crew could tolerate. It can arrive without braking. It can lose one craft if a swarm contains many. It can be designed around a single objective, survive long enough to look. And even that is difficult. The most unsettling part is that none of these problems requires exotic physics. No warp drive is needed. No wormhole. No violation of relativity. The challenge comes from ordinary matter obeying ordinary physics at extraordinary speed. Hydrogen, helium, dust, magnetic fields, radiation. Things that seem almost harmless here become mission-defining when you cross them at a fifth of light speed. That changes how we should think about Alpha Centauri. It is close enough that we can imagine sending something there, but far enough that every piece of engineering is pushed toward an edge. Perhaps that is why Webb's faint S1 candidate feels so strange. A telescope near Earth may be showing us a possible world that light can reach in 4 years, while our machines would need technologies we have not yet built to cross the same gap in decades. For now, the photons are still the fastest explorers we possess. They leave Alpha Centauri A, cross the interstellar medium without asking permission, and arrive at our instruments carrying information about whatever was there years ago. And in the final part of this investigation, we have to ask what those photons have actually earned us. Not what we hope Webb found. Not what a future mission might find. What we can responsibly say today about the mysterious object around the nearest sun-like star, because after 14 chapters of possibility, the answer is both smaller and more extraordinary than the headline suggests. The headline asks a simple question. What did James Webb find around Alpha Centauri A? After everything we have followed, the most accurate answer is surprisingly careful. Webb found a faint infrared point source. It may be a planet. It is not yet a confirmed one. In August 2024, Webb used MIRI's 15.5 micrometer coronagraph to suppress the glare of Alpha Centauri A, after the team also modelled and removed contamination from nearby Alpha Centauri B. A compact source remained about 1.5 arcseconds from A, roughly 2 astronomical units in projected separation. The source, S1, had a measured flux of about 3.5 millijanskis, and was detected at a significance of roughly 3.3 to 4.3 sigma, depending on the analysis. That is the thing Webb actually found. Not an Earth, not an inhabited moon, not proof of life. A point of thermal infrared light. And yet that small result may be enough to open an entirely new chapter. The team attacked the obvious alternatives. Their tests indicate that S1 is neither a normal foreground object nor a distant background source. They also found it unlikely to be a straightforward detector or point spread function subtraction artifact. That is why the planetary interpretation survived. But surviving is not the same as winning. When Webb returned in February 2025, S1 was not detected. When it returned again in April 2025, the source was still absent. A confirmed planet needs repeatable evidence, so the scientific result remained exactly what the study called it. A candidate giant planet. The disappearance sounds like the end, until orbital motion enters the story. A planet does not stay fixed beside its star. It moves. And Webb's coronagraph does not provide equal sensitivity everywhere around Alpha Centauri A. A real planet can travel into a region where residual starlight and the geometry of the coronagraph make it difficult to recover. That explanation becomes more interesting because of C1, the earlier candidate seen by VLT NEAR in 2019. If C1 and S1 are the same physical object, the two detections can be connected by families of dynamically stable orbits with periods of roughly 2 to 3 years. Under those allowed solutions, the researchers calculated about a 52% chance that the candidate would have fallen into poorly detectable regions during both of Webb's 2025 follow-up observations. That number does not mean the planet has a 52% chance of being real. It means the non-detections are not fatal if the C1 plus S1 orbital interpretation is correct. That distinction is the difference between evidence and wishful thinking. The physical model is equally tantalizing. If S1 is a planet, the published analysis allows a temperature near 225 Kelvin, a radius roughly 1.1 times Jupiter's, and a mass around 90 to 150 Earth masses. Its candidate orbit is eccentric and appears substantially tilted relative to the Alpha Centauri binary plane. In plain language, it could be a cool giant broadly in Saturn territory. And its possible path crosses the habitable zone region around Alpha Centauri A. ESA notes that, if confirmed, it would be the closest planet to Earth known to orbit in the habitable zone of a Sun-like star. But because the candidate itself is a gas giant, that does not make S1 a habitable Earth analogue. The excitement comes from the architecture. If a mature giant planet exists around the nearest Sun-like star, then planet formation clearly produced a substantial world there. Its gravity would help determine where smaller planets could survive. Its existence would give future telescopes a real map to work around when they search inward for rocky worlds. Webb also found something by not finding it. Across the observations, the team reached sensitivity to warm exozodiacal dust at only about 5 to 8 times the level of our own zodiacal cloud, and detected no significant extended dust emission at that level. The researchers described this as the deepest exozodiacal dust sensitivity yet achieved for another stellar system. That means the inner Alpha Centauri A system does not appear to be buried inside an overwhelmingly bright, warm dust cloud. For future direct imaging, clean darkness is valuable. A rocky planet around another sun would already be extraordinarily faint. Bright dust scattered through the same region would add noise and confusion. Then we reach the date that makes this investigation unusual tonight. The 2025 orbital study identified August 2026 as an especially favourable period for attempting to recover S1 if the candidate follows the stable C1 plus S1 orbital families. For many of those solutions, the predicted separation exceeds roughly 1 arcsecond and places the candidate away from troublesome boundaries in MIRI's coronagraph. And today is August 15, 2026. As of this date, the latest public official material I could verify from ESA, Webb and STS-SCI still describes S1 as a candidate, while the published orbital analysis identifies August 2026 as the recovery opportunity. I could not find a public announcement yet confirming that S1 has been recovered. That last point is an inference from the public record currently available, not proof that no new observation has been taken or that no unreleased analysis exists. So the story is still open. And the scientific test is beautifully simple. Look again. If a source appears where the orbital solutions predict, the case becomes dramatically stronger. The 2019 detection, the 2024 Webb detection, a new recovery. Separate points could become one gravitational curve. Then the dot becomes motion. Motion becomes an orbit. The orbit helps reveal mass, and mass turns a candidate into a physical world we can begin to understand. If Webb instead sees nothing where it should have strong sensitivity, many planetary solutions will weaken or disappear. S1 could turn out to have been a more complicated artifact or astrophysical feature than current tests reveal. Science loses nothing from that result. The mystery becomes smaller. The method becomes stronger. That may be the most important thing James Webb has found around Alpha Centauri A so far. Not certainty. A testable possibility. For decades, the nearest Sun-like star was an almost irresistible blank space. We knew planets could plausibly exist there. We developed instruments capable of reaching deeper into its glare than before. Then, for one observation in August 2024, something appeared, more than 10,000 times fainter than Alpha Centauri A. Cold. Compact. Close enough to occupy exactly the planetary neighbourhood astronomers wanted to investigate. Then it vanished. And instead of ending the investigation, its disappearance produced a prediction about where gravity should carry it next. That is where we leave Alpha Centauri A tonight. More than 4 light-years away, 2 sun-like stars continue their long orbit around one another. Somewhere near one of them, there may be a cool giant moving along a path we have only partly reconstructed. Or there may be nothing planetary there at all. We do not get to choose. We look, we measure, we wait for the point of light to obey gravity. Because if S1 returns where physics says it should, Webb will have done something extraordinary. The researchers note that a confirmed S1 would be the nearest, coldest, oldest, shortest period and lowest mass planet yet directly imaged around a solar-type star. It would also become the first clear landmark in a planetary system whose smaller worlds may still be hiding deeper in the light. For now, the honest answer remains the most compelling one. James Webb found a candidate, and the universe has not finished telling us what it is.